but this method is useful for systems when you want explicit solvent or if you want to calculate the actual free energy. Mostly people use molecular dynamics to simulate proteins and not really small molecule organics because these methods take too long to get the different conformations out. And so for our group, we primarily use Monte Carlo to do conformational searching, which involves rotating torsions randomly to find all possible conformations. Since you're only rotating the torsions, you don't have to worry about energetic barriers, and you don't have to wait to random movements to find all possible conformations. And so how it works is it rotates the torsion, usually for sp3 type movements, by 120 degrees to find all of the rotations, or if it's an sp2 hybridization, usually 180. So to find all possible conformations, we do 3 to the n. And since only the torsions are rotated, these structures are usually really easy to minimize. Another type of searching is low mode searching, which uses the low frequency modes, and you probe the eigenvectors to find when you spike in energy, and it will continue moving in a downward towards the lower barrier. So these will give like thorough searches of local minimum and can help you find the global minimum since it only travels downward. And so we like to mix the torsional and low mode samplings, and Macromodel lets us do that. So when we do conformational searching, we mix the random torsional movements and the low mode sampling functions. So now Kevin.
So here's how I use the conformational search to determine the feasibility of the reaction. So first it goes by looking at the reaction and running the conformational search, and then processing the data and then confirm it further with the DFT calculations. So this is the reaction that was given to me by Brandon. Hi, Brandon. So this was the macrocycle process or reaction where it had a huge ring formation at the as you can see from the reaction that I proposed that is proposed. The question was, can this ring form, and how can we use this? How can we verify this using conformational search? So the condition was, okay, given the proposed reaction, we first assumed the intermediate where the one of the oxygen was substituted by the nitrogen, and then we assume that the nucleophilic attack will occur next. So in order for this macrocycle to complete, we wanted to see that the distance from the nitrogen to carbon had to be short enough that it's feasible for the reaction to occur. And also we wanted the angle of these carbon had to be near 180 such that the p orbital overlapping will occur. And another thing that we wanted to make sure was this, because we're looking at two cyclic species right next to each other. In case that this is not in the right orientation, we're not going to get the right product that we desire. So on the left, you see what is supposed to be the right product directed reactant, which is when these 4 carbon that is labeled in green are in positive dihedral angle. When it's in negative, as you can see on the right, it's not going to form the right product that that Richmond desired. So in order to understand what we can do about whether this is gonna direct to the right product, what you do is you open a Maestro and import the structure that you designed, which is what you see here. And next, you open up a conformational search tool, which will directly, if you were to run it, it's gonna load the macro model. So first, what I did was load up the amber force field and use the solvent of the non-product solvent, which is chromophore. And use the method of the torsional sampling and perform the basically, and then you click the perform automatic setup, which will put all the parameter of the torsion, angle, bond into the conformational search tool. And you set the number of steps. So for me, I did 100,000 steps for this calculation. And then right here, something that you want to watch out for is the energy window for saving structures, which by default is 21 kilojoules per mole, and that's 5 kilocal per mole. Basically, anything once you're done with the conformational search, anything that goes beyond 5 kilocalories per mole from the lowest energy will be not saved. So if you were to run this, this is what you get. For that molecule, we got about 2,200 conformational search result. As you can see, it's not something that you want to go one by one and analyze. So when you get this many conformers as your result, you want to do more than just using your existing software to analyze them. So what you do, this is what the log file looks like after you run the macro model. Basically, it will do all the conformational search, and every time after it's done with the search, it will save the conformers starting by the lowest energy, and then save all the conformers that goes up to 21 kilojoules per mole. And everything else that goes beyond that energy will not be saved. So even when it's only 5 kilocal per mole that we save, you can see that it still has a lot of conformers that we analyze, which is 2,200 of them. So what do? You analyze them using code. So what I did was I wrote the Python script, which it takes the XYZ file and the atom number as the input, which will calculate distance, which I talked about, the carbon and nitrogen, and it calculates the carbon, nitrogen, carbon, and torsional angle. And once you run this, you're able to analyze all those 2,200 points as you can see here. So what you see here is the torsion to distance from carbon to nitrogen map. This doesn't really tell us anything. What it tells us is that given all the conformers that we have found, there's considerable amount of what we desire on the top, which is positive torsion, and the negative torsion is as much as we found on the positive as well, positive torsion. So this really isn't telling us so much about what will be our desired product or what's more preferred. But we can do more more processing, which by limiting the energy limit to anything within 10k joules per mole, which is only 2.5, which means that we're looking at the really low global low energy conformers. We can process the data much further, which still you can see here, it's not really giving us any distinctive data which can tell us which one's more preferred. And it's not showing here. There's a legend here, which is blue is more negative, more lower in energy, and red is higher in energy. And you can see they're just all over the place. So this, at the moment, what this is telling us is that conformational search tells us that the reaction could happen when the torsion is positive, which is what we desire, or also negative when it's the product that we do not want to have. And if I were to process the data much further by saying, how about if we restrict our conformers to such that it has distance of the carbon to nitrogen less than 4 angstrom and the angle that's greater than 135, that still doesn't really tell us anything, which we could say there exists points in positive torsion, which we desire, which could lead to our favorable product. And this is where you actually do further, you want to do further analysis by using TFT. So from the conformational search, we have found that we cannot draw a very clear conclusion about what we're gonna get as our product. However, if we were to do more computational study on using the FT, which looking at the what we desire on the left and what we do not desire on the right, which is the result of macrocyclization. And if we were to calculate the barriers of these rotation, we found that the barrier from the undesired product to the desired product is only 9 kcal per mole. Thus, even if we do get from the conformational search, even if we get undesired product, the barrier from the undesired product to desired product will occur, will be low enough that all the product will be converted into positive torsion that we didn't have to worry about the negative torsion bits of conformational search result. So this is how you use conformational search, and probably depending on what kind of result you get, you can decide whether you want to do further analysis using TFT.
Okay.
How do you do that?
Oh, you want to get out of the?
Yes, no. I'm gonna go into Maestro.
Why do you
Share. Is it the share?
this one?
Yeah. And so Kevin kind of showed you an automated way of doing conformational searching. In my case, I usually like to do it manually and reformat the parameters that Schrodinger gives you, because they're not always the most efficient or correct. So it can leave stuff out, or it gives you a lot of unnecessary torsion. So I want to make my conformational searching as efficient as possible. Usually because I do this for stereoselectivity predictions, so I need to really make sure I'm getting the lowest energy conformations out. So this is just one of the bisphosphine ligands, and it's got a palladium allyl ground state structure. And so what I'll do under tasks, I'll go to conformational search. And the first thing you have to do is go to potential. Everything I do is done with MM3. I'm doing these solvents in the gas phase, but I can change the dielectric constant to match whatever solvent I am using. And I take the charges from my force field. The other thing you might want to change is the minimization method. I usually use a truncated Newton. All of these methods are in the Schrodinger manual of what they actually mean. So I'll use like a truncated Newton Rapsmith to conjugate gradient to minimize my results. And I'll minimize on the gradient of when that structure is minimized. And then you can actually get into the conformational search techniques. So Schrodinger has a couple of different searching. Torsional sampling, or the Monte Carlo multiple minimum search, is just a random search. You can also do systematic torsional sampling, or this mixed torsional low mode sampling, which we typically do in our lab. And there's other types of sampling as well for more proteins. So I will click the mixed torsional low mode sampling and then perform automated setup. And then usually I'll just display all the markers, and I'll show you what these different categories are. Comparison atoms are just all of the heavy atoms. So usually that's always correct. So you can just get rid of those markers. The next thing that is always marked is the chiral atoms. So usually we don't want our molecules to change chirality during the conformational searching. So it'll mark any of those chiral atoms with an R or S, and it will make sure to check that that is staying chiral. So if you see any of these molecules that say R or S up here, that means it's a chiral atom, and it's going to keep its chirality throughout the conformational search. And the next thing, which is usually the hardest thing for Schrodinger to do, is ring closures. So if you want to rotate any torsion within a ring, you need to break that ring and then rotate the molecule. So you'll rotate that during using that with a ring closure. So the center bond of the ring closure is the one that breaks. So this is where I change all of what Schrodinger does, because it can sometimes do some weird ring closures. Edit this. So if you do edit, I like the ring breaks to be furthest from an important atom. So in my case, my phosphorus is pretty important within the geometry of the molecule. So I want to keep my ring closure as far away from this phosphorus atom as possible. So I will just delete all the ring closures that Schrodinger gives and redo them. So on this ring over here, I'm going to repick the atoms to be as far enough away from this phosphorus. So this is my ring closure where it's going to break this bond over here, and then it will rotate the bonds within this ring. And then again, I'm going to do it on the other side. I also want to be able to rotate bonds within this ring formed by the palladium. So I'm going to keep what they had. So I'm going to have to break one of these palladium phosphorus bonds. Now the next thing is torsional rotations. Schrodinger also puts a lot of unnecessary torsions into the system. And for every rotatable bond you have to do 3 to the end number of rotatable bonds. So to make this more efficient, we want the lowest number of rotatable bonds possible while still being able to get all possible conformations out. So I will get rid of all the unnecessary torsions that Schrodinger puts in. The first couple that Schrodinger messes up with is it'll recount atoms within a ring closure. So if you already have it when it breaks and then the 2 other bonds that are involved in that torsion, they're already rotating when you break the ring. So you don't need to have a separate ring, a torsional rotation for them. So I will delete any of these. So any of these ones in the ring, I will delete. And then I'll only keep the 2 in the ring that weren't described using the ring closure. The other thing I'm going to delete is when you have a bond to a carbon with 3 of the same substituent off of it. So in this case, for the tert-butyl, it'll count that as a torsional rotation, but it's only going to rotate this by 120 degrees. So if it's rotating by 100 degrees, it doesn't matter. So those are going to give out all the same possible conformation. So that's also a redundant torsional rotation that you can get rid of. Macromodel can understand it for just a CH3 group, but for any molecule where you have 3 of the same substituent, Schrodinger won't recognize it. So those also have to be deleted. So I'm going to do the same for the others. But in this case, where you just have one carbon off of it and two hydrogens, this torsion will need to rotate, because if you rotate it 120 degrees, the CH3 group can be in this position, or in this position. So those are all different unique conformers. So these torsions you'll need to keep. So now I'm just going to delete all the redundant ones from the rings that I already described. And now we cut back the torsional rotations quite a bit from what we started with. So now we have 1, 2, 3, 4, 5, 6. Now there's only 9 rotatable bonds, which is a manageable number of steps. So now that I finished this all, I just like to redisplay the markers and make sure everything looks correct. And then you'll click either run or write. I don't run in my terminal, so I have to write all of my jobs. So when I click write, it'll give you a name, and then you'll click the write button. And then I'll show you what these comp files look like. So I have to stop sharing and then
stop sharing.
reshare to that.
Yep, and then go back to share.
So now I will show you what a sample comp file looks like. So when you write a file, it'll give you the Maestro file and then the comp file that it just wrote. And it will have all these different names. The comp are comparison atoms, shake are your chiral atoms, torsions are your rotatable bonds, ring closures are these RC4, mini is the type of minimization you're going to do. And then there's a lot of the LMCS, that is the type of minimization I'm doing. In just as a test, I just put 1,000 steps just to do this quickly. And so this is what your sample comp file will look like. Maestro has a list of what all these abbreviations mean in their Maestro guide. And then afterwards, you'll get a log file that'll initialize the structure, and it will minimize on the force field and give you out an energy. And then we'll go through, and if it's a unique structure, it will get it'll be stored as a structure. If it's the same one, it'll get rejected by that starting structure, or if it's too high of energy, it will also get rejected. So it'll go through all of those Monte Carlo steps, and at the end, it'll give you your output. So just doing 1,000 conformations of this molecule, I got out 11 different conformations, and it took about 15 minutes to do this search. So that's how you do the automated version of Monte Carlo conformational searching.
All right, questions? I see.
Yeah, we had a couple of questions. One just being, how do you choose which force fields to use? I know, Kevin, you used amber, and then you used MM3, and I'm just like, as an organic chemist, not really sure how you would pick. I know some are made for organic molecules and some are more universal, but are there different levels, and how do you? I'm sure this is a big question.
Yes.
Yes. MM3 is fit to be able to reproduce organic molecules, and we actually add our own. So we parameterize our force fields to be able to reproduce usually transition states, and since we involve catalysts, we have metals in there as well. So anything around the metal center and usually around our reaction coordinate, we actually fit any of those parameters. And MM3 we found to be the best at describing organic molecules.
Yeah.
I used Amber because at the time when I was running your structure, one of the atom type was not available, so I had to use whatever that was available at the time.
It was like the sulfur or something.
Yeah, something that so MM3 didn't. I used the default atom type that was available by Macromodel, and I figured that doing conformational search, it wasn't going to change that much of a result for the reaction that we were doing.
And if you can pull it off for small molecules, MM3 is usually a reasonably good choice.
Sure.
Unless you run into the problems that Kevin did. So you don't have the parameters for what you're interested in. At that point, you have to decide, okay, do you generate the parameters yourself, or do you go with what's available? One warning, though, what you can't do, even though you see that occasionally in literature, you can't mix and match. So you can't say, oh yeah, I don't have, that sulfur in MM3, so let me get the parameters out of amber and plunk them into MM3. No.
Okay. So it's not like DFT where you can borrow a different basis for a heavier atom or something.
No, I mean, strictly speaking, all these force field parameters are entirely made up. And the reason they work is is that there's a lot of error cancellation going on. So they work within the context of what they've been parameterized to do. But then you start mixing them and all these errors don't cancel anymore and bad things happen.
The other question we had was on some of Kevin's structures, just about this 180-degree bond angle between the C and C bond. We were unsure why. Can you remind us why you were looking at 180 degrees?
So I originally thought that that angle had to be required for the. So N has the p orbital. So I should have really looked at the angle of the p orbital and then the angle of the atoms that was sticking out from the nitrogen, but I don't think it really it's not really 180 that we're looking for. It's really how p orbital is sticking out in towards the carbon atom that we have to attack. So I don't think it was really required. If I wanted to do more study, I will probably run HOMO and LUMO calculation on the conformers that we have found, and see if the LUMO or the HOMO orbital is actually pointing at the are overlapping such that it will lead to the formation of bond.
So it's basically a surrogate for the backside attack.
Yeah, but the angle that he had shown, if we can go back to that slide, was like a C and C angle, and we were expecting, the nitrogen, carbon, and then leaving group oxygen, which is like a mesylate, I think, angle. And so we're a little bit, I think it's a couple of slides back. Well, maybe not a couple, more than a couple back. Yeah, right here. Yeah. So the angle that's being indicated, that's a dashed blue line, right?
Yeah.
So I guess we would have expected the angle.
Was it supposed to be?
Would be actually around the dotted red line.
Exactly, and the mesylate, right?
So NCO essentially.
Yeah, that's what we would have expected.
As long as the p orbital is pointing in that plane.
Yeah.
Well.
Right. And presumably, these are reactions that will be run with the deprotonated material, actually.
Yeah.
So there will be two lone pairs on nitrogen at that stage to contend with. So I like your idea of looking at the HOMO of the system and the LUMO, and maybe that would provide further insight. Yeah.
We can run that.
Yeah.
I mean, the thing is, once you got the conformations, all this analysis is seconds.
Okay.
Thanks.
Yeah. Do we have other questions? And so, okay, so you mentioned this idea of all these other analyses are seconds. So just in general, I guess I'm curious about times and timelines. So how long does it take to do, for example, the conformational searching to ultimately arrive at those 2,200 conformations, Kevin, using the Amber type approach?
Is that in second?
Yeah, those in seconds. So that's 77,000 CPU seconds.
Running one course, that's real.
So it's about 20 hours
But
on a single CPU.
but I did run 100,000 calculations.
And probably goes.
Yeah, and just out of curiosity for the students, you know, so I noticed there was a palladium complex, and Kevin, you were working on this organic molecule. And so how do you gear up to then do these computations? I mean, do you have to go read the literature on what people have in terms of whatever system you're going to be studying, or, you know, how do you get going?
Well, I think reading the literature is always a good start, isn't it?
Yeah. I guess it depends on what you want to do with the conformational searching. I do serious selectivity predictions. I really need to look at the literature and look at what kind of systems are people doing experimentally, so I can make those kind of predictions, and like model my systems after what they're looking at and understanding the essentially understanding the mechanism of the systems. But for Kevin, I think it's a little different.
I'm more of a I make things automatic. Yeah.
But in general, I mean, the how to do it, Schrödinger, one of the nice things about Schrödinger is that they actually have some pretty good tutorials. So for the students, if you want to get started on you know, doing any of that sort, the tutorials within Schrödinger are pretty good starting point. Just, you know, how do you do certain things, but then, for example, which force field would be best for your specific system? Yeah, literature.
But the automated setup in Schrödinger is good enough for any beginners to use it, and it doesn't take much effort to like just do a confirmation.
You may want to, or you're probably going to waste time by doing the automated setup, but
That's why I ran 100,000.
yeah, that's when you go in with a brute force. But when you do, you know, when time actually starts becoming an issue, you can actually accelerate this quite a bit. Any other questions?
I guess we were just discussing something, but the ring kind of closure approach, I guess that'll only work for force fields, right? Once, like, if we were to use something like the Grimmer XTB or something like that, I guess you can't kind of break bonds in the same way, right?
Well, this is just for the proximity approach. You still could do the conformational sampling using any energy function that you care about.
Yeah, sorry, I meant sort of the idea about sampling a ring by sort of choosing a bond to break, doing a torsional kind of scan, and then sort of reattaching the bonds or something. Like, I think it requires a definition of bonding, right? Like a harmonic potential to snap it back shut again. And
correct. I mean, that's how the Monte Carlo code is written. You would have to, you could probably do similar things by doing Cartesian Monte Carlo and then using distances.
But I guess I guess it comes back to something that we, and I think Matt's group, have noticed, that the ring sampling with things like XTB is going to be the really hard part, because you can't do this sort of classic break a ring apart and sample the open chains and then reattach them kind of thing.
No, I mean, the problem is Schrödinger is ridiculously expensive.
Yeah.
And all of that, but it actually does have some nice tools in it.
True.
And that's one of them that, you know, you with other Monte Carlo searches, you can't easily do. And so you're wasting a lot of CPU time. So, you know, if a programmer is terribly bored, I'm sure you can probably implement it into things like Cassandra or so, but it would actually, because all the stuff is published, it just would require a significant effort. But it does have some nice features in it. All right, anything else? Well, thank you very much. And then let me switch over to the other one.
Thank you, guys.